Good morning and welcome back. Today we're going to be looking at section 5.1, beginning chapter 5, where we start to deal with nonlinear functions. This is going to include parabolas, power functions, and a couple different other types of functions as we get further into this section. Today we're going to be looking at quadratic functions, or if you've heard that word parabola, everything that goes along with them, including exponents, including coefficients, including properties of the graphs, x and y intercepts, all of these things. So let's go ahead and get started, and we will explore what a quadratic function looks like. The first thing I want to do is really look at this graph so we have an idea of what we're solving for later on in the day as we solve for things. There's 5 main things, so you could talk about even way more things with parabola, and you get into slope, and you get into slope at any given point, you get into average rate of change, but the main 5 things we want to look at today are the axis of symmetry, which is where this parabola can be reflected across a line. It could be shifted over, like the case of this one. It could co-align with the y-axis. That just depends on the function itself. That would be this red line right here. We want to look at the x-intercepts. That is where the parabola intersects with the x-axis. Good common note is there could be 2. There could be 1 in the case of this red parabola right there, or there could be 0 in the case of that parabola. But there will be some sort of way to solve for x-intercepts and see how many you have. We have a vertex, also known as h, k. If you hear us talk about that later, the vertex is denoted by the variables h and k. Not the same thing as a, b, or c. These are 2 new variables that are going to apply just to the vertex, just to quadratic functions. And then we've got the y-intercept, which is solved exactly the same way we have before by plugging in 0 into your function, or f of 0. All right. Let's keep moving, and we will see 2 different forms of this equation. And one of these looks a little more common. You're probably really familiar with this one, this x squared. It's like, I don't know if you've ever seen something that looks kind of like, here's an example, 2x squared plus 4x minus 1. It looks like those things we were factoring earlier in the year. It's a pretty common type of equation with pretty easy coefficients and solvable with a quadratic formula, or solvable with factoring, solvable with slide and divide, the AC method, whichever way you've learned to factor those quadratic equations. The second way is a little more informative and a little different. You'll see there's that h and that k. You'll notice a negative sign hanging out in the middle that's flipping the sign of the x coordinate. The h stands for the x coordinate of the vertex, and the k stands for the y coordinate of the vertex. And one really important note is look at that a and ask yourself the question, well, why did they use the exact same variable in these 2 equations, even though they're different equations? And we didn't keep b or c, changed them to x and k, or h and k, but we kept that a value. And a really important note is once you've got your a value, that's going to be the same value in both terms. You're going to factor it out, and you can solve for the exact same a value in both terms, whether you're completing the square or however you solve this. Your a should be the same, because all that's going to happen when you distribute this a is going to go straight to that x squared term that goes right there after you FOIL, and you'll get ax squared. All right, so let's use all these properties. I know that was a lot at once to start solving some problems. So here we have a guy shooting a basketball, the classic form of a parabola. We've got ourselves a vertex. I'm going to do a different color. We got ourselves a vertex, it looks like up here. We got ourselves an x-intercept already. That was nice of them. And then without even looking at the problem, I'm just going to say, well, I think I could probably use this axis of symmetry to find the other x-intercept without even looking at the problem. If you go over 1, 2, 3, 4, and then you go over another 1, 2, 3, 4, we are going to have another basketball landing right there, given that there's no air resistance or drag or friction or anything like that, or wind. And we could probably do the same thing for a couple more points too. If we found some nice, neat points on this graph, so let's say this one looks almost nice and neat, though it looks a little low. See that ball right there? I'm going to go over 1, 2, 1, 2, and I'm going to draw the same shape right there. Looks like it's a little bit like that. And then if I wanted to do it one more time, we could, or we could just try to match that arc as best as we can and ask ourselves the question, does it look like he makes the basket? Because I think that's the question they asked us for the first one. Does it look like he makes the basket? Does the shooter make it? No, he doesn't. It doesn't look like it. Maybe he makes that other one way there in the background, but no, he does not make the basket he's shooting at. All right. Second question that it asks, which is a little tougher, it says find the equation of the path of the ball. And well, they've already given us one really important thing. They've given us this highest point. They've given us this, oh, that's hard to see. They've given us this h, comma k, or this vertex, which is -4, 7. And so I'm going to use that and my first function to start this problem off. And I'm going to say, okay, if you remember from up above, see if you can recall it without looking. A x minus h squared plus k. I'm going to go back and check because sometimes I make mistakes. Often I make mistakes. That is that standard form of the quadratic up above. That vertex form, sometimes you'll hear it called because it shows you the vertex. And now I'm just going to plug in my vertex and go f of x equals a times x minus, what was the point? It was -4, minus, careful with that negative sign, and -4 squared plus 7. That minus a -4 is going to turn into f of x equals a x plus 4 squared plus 7. And now we've got ourselves a little problem. We don't know what a is. We don't necessarily know how to solve it. But if we were to use some context clues and look at our graph, we could say, well, hang on a second. This point might be a pretty easy one to try because it's 0, 0. So what if we use the fact that this is x1, y1, or some random x point on our equation, 0, 0, and we just plugged and chugged it in. And we said, okay, well, if I plug in 0 into my function, then I should get output another 0, or the point x is 0 and y is 0, or x is 0 and f of x is 0. And now, given a one-line equation with one variable, we can totally solve that and see what we end up with. So we'll do the classic draw a line. What you do to one side, you have to do to the other side. And we'll end up with -7 equals a times 4 squared. And then 4 squared minus 7 equals a times 16, which means -7 over 16 equals a. Kind of an ugly fraction, but it's just a fraction. I think we're done. If we plug that back into our original equation, you get f of x equals, I'm going to put parentheses, be careful with that negative sign and that fraction, x plus 4 squared plus 7. And we got ourselves an equation. All right, that was a pretty tough one to get started. It's a good practice, though, in seeing that you can use the vertex form, the vertex and a point on the parabola, to solve for a function given a graph. Take it a little bit easier now. They're giving us a function, and they're just asking us to write the general in the standard form. First thing we're going to do is write the general form because it's just moving it around to be in the right format. So what they've done is they've put the constant term here, and they put the single exponent here and the double exponent here, and they just messed it up. All we're going to do is fix it, being really careful with our signs. We're going to say the laws of commutativity of addition allow us to do that, and we got ourselves a general form. Standard form is a little tougher. Standard form, we got to find the vertex. But the nice thing is they've given us a sweet formula. We could also complete the square. We could also complete the square to find the vertex, which is using the properties from the quadratic equation section of this, or quadratic formula section of the book back in chapter 2. But I'm going to show you a new way to do it, where you know that the h value of the vertex is -b over 2a. And you might be asking yourself, doesn't that seem a little familiar? Isn't there another formula that kind of sounds like -b over 2a? It's like -b plus or minus the square root of b squared minus 4ac all over 2a. So if you can remember the quadratic formula from back in the quadratic section, and you can get rid of the discriminant and get rid of the square root, and in your mind be like, okay, quadratic formula but without the discriminant, then you've got yourself the x coordinate of the vertex. X coordinate of vertex, which has a variable that we call h. All right, so we've got ourselves an a and we got ourselves a b, so I'm going to solve for h and say h is equal to -b over 2a, not all the discriminant, just that part. So it'll be a -6 over 2 times 1. Remember, this is a, b, and c. So we're left with 6 over 2, which is 3. So our x coordinate of the vertex is 3. How do we find the y coordinate of the vertex, or the k? Well, if you have any x value and you want to input it to a function, you can get the output by plugging and chugging it, right? So we're going to go f of 3. Oh, it's g. G of 3 is equal to 13 plus, I'm just using that original equation right there, 3 squared minus 6 times 3. So the g of 3 is going to be equal to 13 plus 9, minus 18. 13 plus 9 is 22. Minus 18 looks like it's going to be 4. 3 comma 4. And so we've got a vertex of 3 comma 4. And we've got ourselves I'm going to move all this over. Give us some more room. Standard form, if you remember the equation for the standard form, that was going to be f of g of x. I keep messing that up. G of x equals a times x minus h squared plus k. So our a value is going to come from our other equation, which was 1. Our a value over there was 1, so our a value over here is 1. X minus 3 squared plus 4. We got ourselves the general, or the standard form, or sometimes you'll hear it called the vertex form. All right, there we go. We can find both forms of an equation. We can find the equation given a graph. Now we're going to talk a little bit about the domain and the range. Domain's the easiest one. Unless they give you any sort of restriction in the problem, unless they write out a restriction in the problem, the domain, probably the easiest thing, all real numbers. Because if you think about a parabola, any parabola, facing up or facing down, those two arrows on the left and the arrows on the right are going to send it to the left and the right infinitely. And so unless the problem gives you a restriction, like they say, hey, only find it from 0 to infinity, the domain is always going to be the same for every parabola, which is all real numbers or negative infinity to infinity. The range is a little different. The range, we have to find the vertex. You cannot find the range without finding the vertex, because that's either the highest point or the lowest point. And so what I'm going to do here is, they've already given it to us in vertex form. So I know the vertex. The vertex is h comma k, and be really careful with that sign. See that negative sign right there? That is what it's supposed to be. It's supposed to be negative in the formula, so our h value is just that. If it were positive, we might have to flip the sign, but because it's negative, and the formula gives us a negative sign, if we go back up and look, see the formula gives us a negative sign right there. Be really careful. That's a really important mistake that I've seen made a couple times, is to be careful with what sign they give you. So our vertex is going to be 4 over 7, comma 8 over 11. And we ask ourselves, well, is it going up or down? Is this parabola, if I were to draw it on a graph, facing up or facing down? I know the vertex is at 4 over 7, 8 over 11, call it up there somewhere in the positive, in the quadrant 1, because they're both positive. Then I look at my a value, that 2 right there, and I see that it's positive. If that a value is positive, our parabola is going up. I don't necessarily know the y-intercept right now. I don't really know much about it, but I know it's going up. And I know its lowest point is at 4 over 7, comma 8 over 11. And so our range, remember for range, we're looking at the y values. So we're going to start at 8, comma 11 and include it and go all the way up forever and ever and ever. And so there we have our range, which we had to find our vertex, more specifically the y coordinate of our vertex, to solve. So we've got a domain and we've got a range. If it were facing down, if it were negative, we would have started at negative infinity and worked our way up till we got to the vertex. Ooh, fun. Next thing they're going to ask us to do is find x and y intercepts, which you already know how to do because you've been working on these quadratics for a long, long time. You know the 3 different ways to solve them. I think they gave us a quadratic formula here, so we're going to have to do a little review, which is a good thing. So g of x, first thing first, we're going to get it into a good format, equals x squared minus 6x plus 13. I'm going to ask myself, what are the factors of 13? Only 13 and 1. Neither of those combine to make negative 6. And so I'm going straight to the quadratic formula. There's no variable up here, so we have an invisible 1. We've got our a is 1, our b is negative 6, and our c is 13. So if you remember that formula, it was that x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. And so we need to plug and chug some numbers and go x is equal to negative negative 6 plus or minus the square root of negative 6 squared minus 4 times 1 times 13 all over 2 times 1. And that just came from plugging and chugging some numbers in. And now we'll do a little bit of multiplication and addition, reduce this a little bit, and we'll go x is equal to positive 6 plus or minus the square root of 36 minus 4 times 13 ends in a 2, has a 4, carry the 1, 52. Let's check. Don't trust yourself. I'm bad at math. 52, cool. 4 times 13 is 52. All over 2, which is 6 plus or minus the square root of 6 minus 2. That ends in a 2. No, it doesn't. 6 minus 2 ends in a 6 and 10, negative 16. 36 minus 52 is negative 16. All over 2. That is a complex answer. 4i over 2, which is just, reduce the variables. Remember, distribute to both of them, not just to one of them. Division and multiplication work exactly the same way. 3 plus or minus 2i is our x values. So using the quadratic formula, we found our solutions, which was x equals 3 plus or minus 2i. But if you remember back from graphing imaginary and complex numbers, that's not a real solution. That's not a real x-intercept. That's just an imaginary solution. It's not on the real graph. And so though it's a solution, it is a solution to that quadratic equation. It is not a real x-intercept. And so we're going to say none. There are no x-intercepts in this problem. Not an x-intercept, though it's a good solution. Next thing we're going to do is find a y-intercept, which is way easier. Remember, for y-intercepts, all we do is find f of 0. And so we're just going to plug in 0, it's g again, g of 0. Be careful what that is. You're working through the problems. It matters. So we're going to go 13. Yeah, I'll do it up here. 13 plus 0 minus 6 times 0 is just going to be 13. So your y-intercept is 0, 13. And you don't have any x-intercepts. So that uses the properties from quadratic functions to solve for x and y intercepts. That's a big rollover from chapter 2. If you don't remember, go back to the chapter 2 where we did quadratic equations. Not quadratic functions, which is this, but quadratic equations, and practice those solves. There are a lot of different types of quadratic equations. We're going to need them as we get into functions. All right, last thing there is. We've got a picture like this problem because you get to draw a picture. You've got a guy standing on a cliff, and he throws a rock. The cliff is 112 feet high. And he throws a rock down, probably like that, and it hits the ocean somewhere. And they give us an equation for it, for the height of the rock, and they ask us, when does the rock reach max height? Well, that word max indicates something right away, that we're looking for a vertex, right? And we already talked about an equation for the vertex. First thing we're going to do is find h. H is negative b over 2a. And we've got an equation set up already in the right form right here because you got your squared term, your not squared term, and then your constant. There's a 1 right there. So we're going to go negative 96 over 2 times negative 16, which is going to reduce down to 96 over 32 is 3, positive 3. So positive 3 is the x value of the vertex, or the t value of the vertex. So at t equals 3, right? If we're talking about our vertex over here, we've got a t and a h of t. We've got a time and a height of time. If our time for our vertex was 3, because we solved it using that h value, all we're going to do is plug and chug that 3 in to get our h of t value, or our k value. So now we're going to say, okay, well, what is h of 3? What is the height at 3? The height at 3 is going to be, plug and chug, negative 16 times 3 squared. This is going to be a big number. Plus 96 times 3 plus 112. And if you do all that math, you get negative 16 times 9 plus 96 times 3. And u plus 112. And you end up with 256 feet tall. If you need to go off to the side to do the arithmetic, that is okay. You're allowed to do that. So that was our second point of our vertex, 260 feet tall. And last but not least, they ask us, well, where does it hit the ocean? So we found our vortex. This green point up here is the point, 3, 256. At 3 seconds, it gets to 256 feet in the air. But then they ask us, well, let's find our x-intercept. Let's find where it hits the ground. And we talked about the ways to find x-intercept is that factoring. So what we're going to do is we're going to say h of t. I'm going to rewrite the whole equation before we do it, plug and chug. We said there's two things you can find. You can find an x-intercept and y-intercept. You find the y-intercept by plugging and chugging in 0. So if we plugged in 0, we'd get 112. And that would be that y-intercept. That's be where that ball intersects with the y-axis. By setting it equal to 0, we solve for the x-intercept. And then we just use normal math from chapter 2 to solve, where you draw the line and you see what you can do. You can move stuff around. You can divide by the same number. So what I'm going to do first is I'm going to make my life way easier and divide by negative 16. Because all of those terms are divisible by 16. Left with 0, t squared, minus, because of the negative sign, be careful with that, 6t, minus again, because negative sign, minus 7. All right. Now what we're going to do is ask ourselves, is there any factors of negative 7 that make up negative 6? Perhaps we try negative 7 and positive 1. Negative 7 positive 1 works. They multiply to give you c. Negative 7 times positive 1 equals negative 7. That's good. And negative 7 plus negative 1 equals negative 6. That's your b term. Also good. So those are our factors. So we write down below t minus 7 and t plus 1 equals 0. And then those factors give us our solutions of t equals 7 and t equals negative 1. Now we got to decide, wait, they gave us 2 answers and we only wanted 1. So is this number more like 7 or more like negative 1? And we're going to I'm going to sketch this y-intercept real quick. So that is the y-axis with the y-intercept right there, right? If we go to the right of the y-intercept, we get 7. And so when does the rock hit the ocean? Probably be at time equals 7. So what does that negative 1 stand for? Well, if we could reverse time, we could say that guy's not even there and the ball is just traveling in this path, and you could go backwards in time, it does kind of look like this ball would hit the ground at about negative 1 to the left of the y-intercept, though that's not possible because we can't time travel, so we're not even going to consider it. We're going to say that this ball hits the water at time equals 7. All right, that's what we have on quadratics. Thank you for watching. Start practicing these equations before you move on to the homework. Try some of the exercises in the textbook. I appreciate you watching through this far, and I will see you next time.